Hello, and welcome to the lecture for Chapter 24 from Conceptual Physical Science, 6th edition. In this chapter, we're going to talk about the study of the oceans, their interaction with the atmosphere, and the overall effect, which is climate. This is really included in our Earth studies or geology unit of physical science. Up to this point, in the previous 4 chapters, we've been really talking about proper geology in terms of the study of rocks and plate tectonics and layers of the Earth. But the oceans are part of the Earth. They certainly affect rocks and are affected by plate tectonics, but they can be studied in their own right as well. So this is going to be another one of our Earth science chapters, and in fact, our second to last one, because after we talk about the oceans and atmosphere, then we just have to talk about storms and the weather, and we got everything all wrapped up. We can then move on to astronomy. But let's get to the content of Chapter 24. So we're going to talk broadly about Earth's atmosphere and oceans. So we're going to start things off. Then we're going to talk about the components of Earth's ocean. What is it made out of? Then we're talking about physical movement, physical propagation of energy within the oceans. These include waves, tides, and the effects on the shorelines. Then we'll move on to the atmosphere, talking about its composition, talk about solar energy, which is so important for the atmosphere since it's the first contact of that incoming radiative energy. And then we'll talk about the driving forces of air motion. Obviously, being warmed up is going to have a really big effect, but the actual rotation of the planet plays a role as well, which will segue nicely into our final topic of the globular circulation patterns, the big global patterns of circular motion, the Coriolis effect at the global scale, that kind of effect, the jet streams, these large movements of fluid, especially in the atmosphere, but affected by oceans, as well as large ocean currents, will get discussed there. Okay, well, let's get to it. So first, we should start by appreciating the sheer volume of the oceans and the fact that 71% of Earth's surface is covered by water. Water's high specific heat capacity, and that should sound familiar because we talked about heat capacity, and we specifically talked about how water has one of the highest heat capacities in the known universe. That means that it takes a lot of energy to warm up water, a certain amount of water, a certain number of degrees. Okay? But that high heat capacity accounts for the moderate temperatures in coastal lands. Okay? So you can have continental temperatures, they can be much more extreme. The ocean moderates temperature variation. So anything near large bodies of water, in particular the ocean, is always going to have more moderate weather. Earth's early atmosphere appeared before the sun was fully formed. Okay, so in the primordial ages of the solar system. At that point, the planet itself was molten, it was early in formation, and then atmosphere was the retained gas of hydrogen and helium. This isn't like the atmosphere that would have been building up around large comets that eventually became gas giants in the outer solar system. It's just that they were large at this point and thus holding, by their gravity, more hydrogen and helium. Earth only held on to a little, but some of that hydrogen and helium is left today. It's just now mixed with other elements. The sun's formation swept away Earth's original atmosphere, and a new atmosphere formed over time. Okay? It swept away most of it, I should say. Earth's atmosphere developed in stages, and actually we were just talking about the formation of the atmosphere when we were talking about the different periods of the eras of Earth's geological history, because there are points in the biological evolution of organisms on Earth where different elements were introduced in the atmosphere, as well as outgassing from volcanoes. So in other words, we were just talking about that. Let's review it here. So hot gases escape through volcanoes. That was one of the first processes of continual atmospheric creation. And we've seen this on other worlds as well as on Venus. Free oxygen occurred as a result of photosynthesis by early cyanobacteria, okay? Early in the sense of evolutionary. Ozone then began to accumulate in the upper atmosphere, which we talked about was so important for preventing high energy UV radiation from reaching the surface. Eventually, water vapor condensed to form the oceans. So, the ocean floor encompasses continental margins and the deep ocean basin, okay? So the floor consists of those different regions. This should sound familiar as well because when we talked about plate tectonics, we talked about the ocean plates, the thin, much denser plates that make up the ocean, and how they are relatively uniform, so they're flat, and then they dive down in subduction zone, creating trenches, and they raise up where there's mid-ocean ridges, okay? So we can see an example here of a mid-ocean ridge. We can see that long, flat tectonic plate that is the ocean plate in its particular composition, which creates this area called the ocean basin. It is quite deep. It's many kilometers deep, and it's quite flat. Now, flowing from water on land, we can get large structures like deep sea fans, but as we get close to a continent, there is always a continental rise, followed by a continental slope, and eventually we reach the peak where we have the continental shelf. Sometimes, again, due to flow from the continents themselves, we can have these large submarine canyons that cut into the shelf, essentially just driven by erosion, by uniform flows or continual flows of water in one direction. And they basically carry the soil away that then would get deposited somewhere on the abyssal plain, which is a part of the deep sea basin. And by the way, these terms are interchangeable, abyssal plain and deep sea basin. Okay, so the continental margins are between the shorelines and the deep ocean basins. The continental shelf itself is shallow, underwater extensions of the continent. Think of it as just the flooded edges of the continent. The continental slope marks the boundary between the continent and the oceanic crust. And the continental rise is the wedge of accumulated sediment at the base of the continental slope. Notice what is missing in this diagram, and this is an example of one of the big consequences of oceanic crust subduction is there could be a large trench here. Those don't happen at every margin with a continent, but they do happen occasionally. Underwater mountains, well, let's start here, The ocean bottom is etched with deep canyons, trenches, and crevasses. The underwater mountains rise upward from the seafloor. The deep ocean basin, that abyssal plain, is made of basalt from the seafloor spreading. Because how are the seafloor plates created? They're created by continual renewal from the mid-Atlantic ridge, plus thick accumulations of sediment. The abyssal plains, ocean trenches, and seamounts. The deep ocean basin consists of the abyssal plains, which are the flattest part of the ocean floor due to accumulated sediment, basically sifting down through those kilometers of water above. Ocean trenches, which are long, deep, steep troughs at subduction zones, which I mentioned, but were not included in the diagram or in the picture. And seamounts, which are elevated seafloor occurrences, so elevated parts of the seafloor that come from volcanism. Now, seamounts are more of isolated volcanoes within the seafloor because there are spots where some magma reaches the surface. But overall, long, stretching structures of volcanoes are the mid-ocean ridges. These are different in that they are much longer and more substantial. But they also consist of volcanoes, just like seamounts, but instead of just one, many in a line. These are the sites of seafloor spreading. This is one of the driving forces of plate tectonics, and that energy is coming up from the mantle. Volcanic and tectonic activity occur at this point. A global mid-ocean ridge system winds around the Earth, okay? But it's not just one, it splits off into different sections. But you can clearly see that it's almost like the whole Earth is split and constantly turning over on itself at the level of the crust. Now, the deepest parts of the ocean are at the ocean trenches, because of course the trenches are deeper themselves than the basin or the abyssal plain. And those trenches occur near some of the continents. The shallowest waters are in the middle, right under the oceanic ridges, the mid-ocean ridges, okay? That's always the shallowest part of the ocean. We can see an example cutting across the Atlantic Ocean, shown here, going from New England over to Gibraltar in southern Spain. So cutting across the ocean there, we can see examples of seamounts, we can see a flat region of the abyssal plain, we can see the mid-Atlantic ridge itself, and we can even see some islands created by particularly large seamounts. We can see somewhat of a trench here, but an ocean that has more dramatic trenches by far is cutting across the Pacific Ocean, in this case showing a cut and the elevation variation, because that's, by the way, the vertical axis is all just about depth, okay? And so this 2D cut, then showing the Australian continental shelf starting over here, so on the coast of Australia, and heading straight across the Pacific over to South America and the Andes Mountains. We can clearly see that after we leave the Australian continent, we have a trench caused by subduction. On that side of the Pacific, it's known as the Tonga Trench, and as we get over to the other side of the Pacific, we have the Peru-Chile Trench. So, Ocean trenches are the deepest parts of the ocean floor. Why? Is it because that is where oceanic crust meets continental crust? Is it because that is where subduction occurs? Is it because no sediment accumulates there? Or is it because all accumulated sediment settles in the abyssal plain? Well, it's because of subduction, right? Just meeting a continent is not enough. There are examples where the oceanic plate meets a continent and there's not substantial subduction, but subduction can lead to trenches. Okay, subduction of denser tectonic plates under less dense tectonic plates. So, okay, that's the surface, the floor, the land mass of the ocean. But what about the energy propagating through the fluid, the actual water? Well, that takes its form as waves and tides, right? And if we should start then by talking about the characteristics of waves. And waves get their energy from where? From wind. Okay. Now there are exceptions like energy from a volcano eruption, also from a earthquake, so a tidal wave. But the overall energy, the manifestation of that energy is wind. The crest is the peak of the wave. The trough is the low area between the waves. Okay. So crest shown here, and trough shown here. Wave height is the distance between a trough and a crest. All right. So this is the height of the wave, which is twice the amplitude of the wave. Wavelength is a horizontal distance between crests. So that would be the wavelength there, represented by the Greek letter lambda. Wave period is a time interval between the passage of two successful crests. And if these sound like familiar physical characteristics, we indeed had a whole chapter discussing waves. You can go back and review that if you're particularly interested in waves. Height, length, and period of a wave depend on wind speed, length of time the wind has blown, and fetch, which is the distance that the wind has traveled across the open water. Waves of the ocean surface are orbital waves. That means the wave energy moves forward. The disturbance moves, not the water. This occurs in the open sea in deep water. So in other words, the wave travels through the water, it does not carry the water with it. This is in contrast to crashing waves at the shore, because in that case, the water is literally falling under the influence of gravity, and it's just a different physical phenomenon. We can see the circular structures of the waves, and we can see that those circular structures that drive the waves at the surface are also represented by smaller and smaller scale circular structures as we go into greater depth, because that energy gets absorbed in an entropic way into essentially heat energy or the random motion of H2O molecules, and the actual circular structures fade away to nothing, okay? So waves at the shoreline in shallow water at a depth of about 1/2 the wavelength, the wave begins to feel the bottom. Now there is a direct kind of reflection of energy off the bottom, and that's going to change the wave. The wave now grows higher, okay? And we can see when the wave starts to feel the bottom due to those cascading smaller circular structures, becoming smaller with depth that I was talking about. But once they start to influence with the bottom, that energy gets reflected back, all right? And as a steep wave front collapses, the wave breaks. The turbulent water created by the crash is called the surf, okay? So, question. When a wave approaches the shore, the water depth decreases. This affects the wave by flattening its circular motion, decreasing its speed and increasing the distance between waves and the wave height, increasing its speed and distance between waves and decreasing the wave period, or decreasing its speed and distance between waves, thus causing the wave height to increase, or increasing its speed and distance between waves, thus causing the wave height to increase. So which is it? Well, we knew it's going to be a height increase, and we can reason out that decreasing its speed and distance between waves will then result in that height increase. So, as waves enter shallow water, the forward direction in fact changes. The waves nearest to the shore slow and lag behind the incoming waves. Thus, the incoming waves also slow and begin to pivot. As this continues, the wave crest bends and pivots around the slower portion, the lower portion. This is wave refraction. Okay? Different parts of the wave now traveling at different velocities causes a bending and distortion of the wave. Just like a wave itself, when traveling from one medium to another, gets refracted or bent. Because remember, refraction just means bending. There's also something called the longshore current. Now, this is a current that runs almost perpendicular to the shore, parallel to the shore, where of course waves run perpendicular to the shore. In other words, waves are incoming, but these currents run along the shore. The oblique approach of waves creates flow that's parallel to the shore. So let's show that here. Here we have the effective wave direction, waves coming into a shore. But that creates this current that we see runs along the shore. And you can think of this just as the result of the fact that that circular motion that we saw and perhaps seems reasonably associated with a rolling wave, well, that circular motion is not, in fact, entirely two-dimensional. And it's that three-dimensional effect, that component of the circular motion, that means that there is some leftover energy that's going to essentially roll along the shore. And this picture also shows that affects the sand, creating beach drift, because it's that same energy, and then the sand molecules are more likely to get pulled in that same direction. The impact of wave refraction on shorelines means that wave energy is unevenly distributed. It's concentrated in headland areas, which then end up being areas of high erosion, and it's diluted in the adjacent coves and bays, which are areas of deposition. So then that means the waves are simultaneously playing the role of eating into the land, but also depositing land. And so over time, regions of the shore will grow out into the ocean, whereas other regions of the shore will get gradually eaten away by the ocean. And we can see examples of that here, where we have wave energy that's concentrated at these points because it's converging. That's going to create a lot of this erosion, eating away of the land. But then we can see waves that have very low energy here. That very slow moving water means that larger particles are able to settle out of the water, and we have ourselves some deposition. So the characteristic coastal erosional landforms look something like this. We have a wave-cut platform, which is shown up here, right, creating these terraces. We have sea cliffs due to the erosion. We can get sea caves that fill up with the tides. We have sea arches, where particularly strong pieces of rock remain and then are held together up at the top. But eventually all sea arches do collapse. And we also have rock that's left over, and perhaps left over just because of the overall effect of the wave direction, as we saw varies. This could be a region where most waves are being refracted away from this point, so it's allowed to survive, or perhaps the rock was just stronger than the surrounding. As far as the deposition and the landforms associated with deposition, such as in the calm bays, we end up with beaches, splits, which are shown here, right? They're like long beaches that stick out as without any actual building up of substantial amounts of land. We have lagoons that form behind enclosed spits. We have barrier islands that are composed of spits and larger pieces of land. And we have tidal inlets, such as the entrance to a bay. Coral reefs, obviously near shores, not in the deep ocean, are composed of actively growing coral organisms. Organisms that secrete calcium carbonate as they grow, and this is what we see. Just like the stromatolites of the Precambrian phase excreted calcium carbonate, being the first animals to evolve the ability to do that on our planet, and left a fossil record for us, the coral of today is doing the same thing. Many reefs survive on photosynthetic algae. This is what's called a symbiotic relationship, and it means that coral does have to be near the surface because it can't be so deep that no light energy reaches. Coral bleaching is an indicator of global warming because it's changing the pH level of the oceans and thus causing that bleaching effect. Now, what about the tides? Because obviously when we think of oceans, one of the first things that come to mind is the tides. Well, tides occur because of the difference in the gravitational pull exerted by the moon on the opposite side of the Earth. Okay? So the tides are because the Earth pulls on the moon, but due to Newton's third law, that means that the moon pulls on the Earth with just as much force. Now the Earth is much more massive, so it doesn't cause the Earth to orbit the moon like the moon orbits us, but it does pull on the less strong, more easily deformed portions of the planet, which is essentially our oceans. And so that pull from the moon means that the oceans get tugged with the moon, creating tides. There is always a high tide on the face of the Earth that is directly facing the moon, and the exact opposite side. Okay? But because the moon moves around Earth, the times of the tides vary each day. Okay? How long does it take the moon to make a complete orbit around the Earth? About 27 days. That's where a month comes from. Furthermore, alignment of the sun, Earth, and the moon causes spring tides, which are more dramatic. So that means that during full moons and new moons, because those are the only times that the Earth, Moon, and Sun make a line like this, because that's either going to be a new moon, which is this one here, or a full, depending on how much light, either none in the case of a new moon, or maximum amount in the case of a full moon, is reflected from the surface of the moon and visible from the surface of Earth. Okay, because that's what new moons and full moons are all about. Now, the point being that when we have this alignment, well, when we have more dramatic tides. In other words, high tides are higher and low tides are not as low, okay? However, when we have perpendicular orientation between the moon, the sun, and the earth, well, now we have what are called neap tides. This means the highs are not as high and the lows are not as low. And excuse me, back here, I should have said that the lows are lower and the highs are higher, because it actually does affect both ends. All right, so excuse me for saying that incorrectly a moment ago, but here in the case of neap tides, indeed the high tides are higher and the lows are not as low. Okay, excuse me, the highs are not as high and the lows are not as low. So instead of having, say, an 8-foot high tide, you might only have a 5-foot high tide. Okay? And point being is that this is because we have a gravitational tug in one direction from the moon and then a different tug in the other direction from the sun. The overall effect is that, well, they don't really contribute to each other. They're not canceling out, but they're not adding up in the same way as before, where the forces were all in a line. All right, these are all the forces, the gravitational forces. Okay, well, what about the Earth's atmosphere? Okay, we're done talking about the ocean. We've acknowledged its composition. We've acknowledged the way it interacts when it hits the shoreline in terms of its waves and how it gets pulled side to side in tides throughout the month. But now let's go up into the sky and talk about the atmosphere. Well, the composition of the atmosphere includes the following chemicals in percentage by volume. Okay, so that means that the atmosphere, if we look at this table, is mostly nitrogen, right? So percentage by volume of nitrogen is 78%. The next most common molecule in the atmosphere is oxygen. Do notice that both nitrogen and oxygen are diatomic. The third most common element in the atmosphere is the gas argon, then neon, and so on. So we can see that by far, most of the atmosphere is nitrogen and oxygen. Things like helium or hydrogen make up a tiny amount of the atmosphere. And water vapor even makes a tiny amount of the atmosphere. Ozone does as well, but of course it has a very important role to play. We don't need that much in order to absorb a lot of UV radiation. So Earth's atmosphere is divided into layers, each with different characteristics. So it's important that we understand these different layers, both which ones are higher up and what they do. We will talk about these layers as the troposphere, stratosphere, mesosphere, thermosphere, ionosphere, and finally the exosphere, which is almost no atmosphere at all because it's really high. This is in order from going from the ground up. The troposphere is the lowest and thinnest layer. It is about 16 kilometers at the equator and only 8 kilometers at the poles. Now, that is as high as any mountain, but still, that's not very big compared to the overall atmosphere. It's 90% of the atmosphere's mass because it's much, much denser than the atmosphere above. That's because the atmosphere, being a gas, essentially compresses itself, creating a very big density variation with a much denser atmosphere at the bottom and a very low density atmosphere as we get higher up. Water is not like that, by the way. If we vary a similar number of kilometers and delve into the deepest parts of the ocean has not become appreciably denser, only a tiny bit more. And that's because water is a liquid, and liquids don't condense in the same way gases do. Well, continuing on, this is where weather occurs. All clouds, or at least a vast majority of clouds. Certainly this is where dominant kind of weather that affects the surface. Rain clouds would all form within the troposphere. Very, very important effects there. The temperature decreases with altitude. So as we go up in the troposphere, it gets colder and colder. We know this because mountaintops are known for being very cold. This has to do with the fact that we're getting above the reflected energy of the Earth's surface, and we're simply getting into colder and colder regions. Okay? It's also because the density is decreasing pretty appreciably within the troposphere itself, and that's also going to mean that the upper parts of the troposphere just can't hold as much heat, but that would be perceptible, thus they're going to feel colder. The top of the troposphere has an average temperature of negative 50 degrees Celsius, so quite cold. Above the troposphere, is the stratosphere. The top of the troposphere is so it starts at the top of the troposphere, right? Obviously, because it meets it, and then it continues up to what's considered about 50 kilometers. That's the end. Up in the stratosphere is where the ozone layer is created, or excuse me, is contained. This layer of ozone, right, just a few molecules really, but very important, absorbs harmful UV radiation. Here, the temperature actually increases because of the ozone absorption of UV radiation. That means that the temperature there is colder at the bottom where it meets the troposphere, and then actually warms up, not to a warm temperature exactly, but up to 0 degrees Celsius. Now, if you were to travel to the stratosphere, would you feel that warming? No, because now the atmosphere has become so low density at a height of 50 kilometers that there's just not that many molecules making contact with an object like a human body, so it actually wouldn't keep you warm, even though the temperature has become higher. But then we can continue up further into these higher regions of the atmosphere. At this point, we are essentially going out of areas where a plane could generate lift easily. We're getting into regions where only really rockets travel through on their way to space. But of course, although that means that we can't navigate this part of the atmosphere, it still plays a very important role in affecting the planet as a whole. Okay, so continuing up into the mesosphere, we have it starting at the stratosphere, of course, and then continuing up to an altitude of 80 kilometers. Here, the temperature decreases with altitude again. The gases in this layer absorb very little UV radiation, so they're not picking up more radiation, unlike the ones in the stratosphere. It's 0 degrees at the bottom, and it becomes quite cold at negative 90 degrees at the top, and an incredibly low density. All right. Above that is the thermosphere. Now, thermo, of course, means warmth, and which might be the last thing on your mind as we're approaching the edge of space. Of course, space is incredibly cold. Well, why is it called that? Well, because actually the temperature does go up dramatically in the thermosphere. The temperature increases with altitude. The temperature is related to the average speed of gas molecules, and therefore, right, because that is after all the definition of temperature, therefore the very high speed gives by definition a high temperature, right? High speed means high temperature. The temperature actually goes up to 1500 degrees Kelvin. I mean, that's above the melting point of many metals. How can it be that hot in the upper atmosphere? Well, it's that hot because there is high absorption of X-rays. Just like in the stratosphere where gases are absorbing UV radiation, X-rays, which are just higher energy photons, are getting absorbed by the few gases that exist up in the thermosphere. But let's remember that the very low density up there, as I said before relating to the stratosphere, means that the gas molecules have very little heat in them. So it would feel freezing cold even though this temperature is exceptionally high. There's just not that much energy. There's just a few very fast molecules, okay? So technically a high temperature, but very low heat. But also an important role for absorbing X-ray energy up there, because obviously it's preventing X-rays from coming down to the surface of the planet. Above this is the ionosphere. This is the electrified region within the thermosphere and the upper mesosphere. This is where auroras occur, which are fiery displays of light near Earth's magnetic poles. So the whole idea with the ionosphere is it's charged up because of the permanent magnetic field of Earth and then the trapped charged particles that then are swirling around that magnetic field, creating an overall charged region of the atmosphere. Above the ionosphere is the exosphere, which is basically just the edge of space. We can call it the interface between Earth and space. And beyond 500 kilometers, there's essentially no atoms or molecules, and therefore they that are being held by Earth, and therefore they all escape into space. So then we have truly no retained gas, so we could then say at some point we're absolutely in space. But for all intents and purposes, anyone would consider many altitudes below 500 kilometers also space. Case in point, many satellites actually orbit below 500 kilometers. The International Space Station orbits at an average of 350 kilometers above the surface of Earth, so technically within the exosphere. But there's, again, just a few molecules up there, so there's no appreciable friction. Here is a graph that actually shows that average temperature of Earth's atmosphere that zigzags with those different regions. In other words, we can see it decreasing within the troposphere, the part of the atmosphere that all life lives in, then gradually increasing in the stratosphere due to UV radiation, decreasing again in the mesosphere because of a lack of any type of absorption, and then finally rising dramatically in the thermosphere due to absorption of higher energy photons. And we talked about how the thermosphere has high temperature because there's fast molecules, but it wouldn't feel warm. By the way, when you see spacecraft re-entering Earth's atmosphere and they're burning up on re-entry, that's not because they're traveling through the hot thermosphere. They're burning up once they travel into the stratosphere, and the actual number of molecules starts to increase dramatically. Solar radiation, okay, is going to affect the atmosphere. What is it? We talked about it before when we talked about heat flow. It's one of the 3 ways that heat can flow. But solar radiation is electromagnetic energy that's emitted by the sun. Visible short wavelength radiation is part of it, but there are other types of radiation as well, including ultraviolet or infrared radiation. Terrestrial radiation is re-emitted solar radiation from Earth's surface. That type of radiation is, case in point, infrared, which means it's longer wavelength, lower energy radiation. That's a heat signature. Not visible to the human eye, but there actually are a lot of biological eyes that can see infrared. Right? Insects, for example. The sun warms Earth's ground. That solar radiation goes somewhere, right? And the ground in turn warms Earth's atmosphere. It re-radiates that energy. And where does that warming atmosphere really occur due to the reflected energy of the ground? Within the troposphere, okay? So Earth's temperature varies according to the degree of solar intensity, the amount of solar radiation per area. Where solar intensity is higher, temperatures are higher, right? So direct correlation there. Solar intensity is the highest where the sun rays strike the Earth's surface straight on, okay? That means that we can consider an analogy like a flashlight beam that is held directly above a piece of paper, in other words, at a 90-degree angle to the surface. Okay, so 90 degree to the surface. That is equivalent of an equatorial region, or a day on the equinox when the sun is directly overhead, okay? Or the solstice, actually. And in that case, you have the most direct sunlight, the most high intensity sunlight that you possibly can. On the other hand, solar intensity is weaker where the sun rays strike the surface at an angle. This is like the flashlight beam hitting at an angle like this. In this case, the angle would be something like this, greater than 90 degrees. In that case, we can see the energy of the light is spread out over a larger ellipse than it was when it was in that bright circle. That spreading out means that you have less energy per square of the paper, right, per square centimeter, or in the case of sunlight, less energy per square meter. Okay, also higher altitudes do decrease the intensity of the light. So variations in solar intensity with latitude and the tilt of the Earth's axis helps to explain the different seasons. It's all about whether the sun is hitting directly or not, right? So we can see in the summer solstice, we have sun hitting directly, but then in the winter solstice, we have sun that is hitting, well, at a very long angle, okay? So when the sun's rays are closest to perpendicular at any spot on the Earth, that region's season is in summer. 6 months later, as the rays fall upon the same region more obliquely, that's spreading out the light, the season is now in winter. In between are the seasons fall and spring. So again, right, we have this idea, imagining, being at some upper latitude, the sun is hitting pretty directly, but then considering in that same point, right, now it's spread out over a larger angle, right, because it's not hitting as directly, okay? Now, of course, at the scale of this picture, it's kind of hard to see, but again, the flashlight analogy, I think, holds that idea quite well. So human activities pump greenhouse gases into the atmosphere: carbon dioxide, methane, nitrous oxide, ozone, and CFCs. The result is a warming Earth. We see lots of evidence of a warming Earth. The atmosphere is changing. The underlying driving force of motion in the atmosphere is unequal heating of Earth's surface. For example, water warming up more slowly than land because of its high specific heat. Also, atmospheric pressure. So the force the atmosphere exerts on the surface of the land. Because the atmosphere, we think of it as just being almost not there, barely able to hold us up. Yes, it can generate lift for planes and birds, but it's not like we can fly, right? Humans can fly. But the atmosphere is a fluid, and there's a huge amount of it. When we sit on the surface of the Earth, it's like we're at the bottom of an ocean of gas, okay? And thus, it's being pushed and pushing on itself with a lot of pressure. At any level in the atmosphere, the force equals the total weight of the air above that level. And these forces are huge. Remember, atmospheric pressure is 100,000 pascals. Well, a pascal is equivalent to a Newton per square meter. That's a lot of force. 100,000 newtons is a huge amount of force per square meter, which is basically a 3 foot by 3 foot block. So the atmosphere really has a lot of force and therefore a lot of pressure associated with it. At higher elevations with fewer air molecules above the atmosphere, the pressure is much less. There's the convection cycle. That means that warm air parcels rise due to the buoyant force, and the cooler parcels sink. This creates a constant cycling of warmer and cooler air. The warm air is less dense than the cool air. So again, it is the buoyant force that will lift those pockets of air up. The convection currents stir the wind. They create lateral motion as well as the vertical motion because the overall convection current is circular. So it can create wind to the side as well as up and down. The wind is air that flows horizontally from higher pressure to lower pressure. The greater the pressure gradient, the stronger the wind. Just like the greater the slope, the faster the stream flows. Pressure differences are caused by uneven heating of the Earth's surface. Local differences in heating can contribute to small-scale local winds, such as a very hot area in a city with lots of concrete. Planet-scale differences occur because of solar intensity variations. Equatorial regions have greater solar intensity year-round than the polar regions. The differences contribute to a global wind pattern, right, with just small variations at the local scale. So, atmospheric pressure is greatest near the Earth's surface. Why? Because of the weight of all the air above? Is it because 90% of the Earth's atmosphere is in the troposphere? Is it because of the warm temperatures? Or is it because of water vapor? Well, it's simply because of the weight. We're at the bottom of a long column of air, effectively, where you're standing. Above you is miles of air, while all that weight is pushing down on the ground. What drives air from areas of high pressure to areas of low pressure? Is it the convection currents? Is it the wind? Is it the pressure gradient force? Or is it the water vapor? Well, of course, the answer here is the pressure gradient force. These other answers, like convection currents, wind, and water vapor, or at least the first two, A and B, are what create the pressure variation in the first place. But once you have the pressure variation, the actual motion is because of a force, because we know from Newton's second law that force can be related to acceleration. That's what gets things moving. So let's think then about the driving force of air motion, temperature-pressure relationships. Well, warm air characteristics mean that warm air expands and thus has a lower density and lower pressure. The cool air characteristics can be defined as cool air that contracts, becomes smaller, and thus has a higher density and higher pressure. That means the cool air sinks and the warm air rises. Local winds essentially mean that not all surfaces are heated equally or are related to that. Example, land heats and cools more rapidly than water, as we spoke about, right? Water has a high specific heat, so it's always going to lag behind land, both in heating and cooling. Unequal heating results in pressure differences, and the pressure differences result in wind. Remember, wind is air that flows horizontally from higher pressure to lower pressure. So, quick check here. More energy is required to raise the temperature of water than that of land. Once heated, water will retain the heat longer than land. This concept is related to what? Expansion of warm air, pressure differences of land and water, water's high specific heat capacity, or the expansion of seawater? Pressure differences, right? Or, okay, well, okay, excuse me. But water's high specific heat capacity, I guess, is because of that lag, right? The fact that it requires more energy, all right? So I would word this a bit differently. I forgot that I wanted to rewrite this problem, but essentially it's maybe a better question to be, what's the underlying explanation of this phenomenon? And that would be water's high specific heat capacity. Because you could say then that this requirement of more energy then leads to pressure differences. But either way, at a hypothetical schoolyard, there's a blacktop area and a grassy area. On a particularly warm day, a small breeze develops. Which way does the air move? Would it move from the grassy area to the blacktop? Would it move from the blacktop to the grassy area? Or would it move from the low pressure to the high pressure? Or do we not have enough information? Well, it would actually move from the grassy area to the blacktop because air above the blacktop is hotter. If it's hotter, that means lower pressure, okay, less dense. Whereas above the grass, it's cooler, which means higher pressure. Air will always move from high to low, so the breeze will blow from the grass to the blacktop. Pretty cool. So on the big scale, on the global scale, what's going on with air motion? Well, we have what's known as the Coriolis Force. This states that moving bodies, any moving body, the Earth being an example, and the air on the Earth, deflect to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection of wind varies according to the speed and latitude. It's most dramatic closer to the equators. Faster wind, greater deflection. The deflection is greatest at the poles and decreases to zero at the equator. So I guess the way to phrase that is, yes, the effect of all the deflection ends up being manifest at the equators, but the initial angle is largest at the poles. Okay. Factors that affect wind. Well, the pressure gradient force, air moves from high pressure to low pressure, like from the grass to the blacktop. The Coriolis force, which causes an apparent deflection of winds due to Earth's rotation. And the frictional force, just saying that air moving close to the ground slows down as opposed to air at higher altitudes. All right, so here is an example of pressure gradient force and the resulting wind. Here's an example of the Coriolis effect in the southern hemisphere and northern hemisphere. And here are some examples of frictional forces with near the ground moving slower than above the ground, creating these circular patterns on a vertical level, right? So this would be like in the y direction, in the vertical direction, whereas here this is looking down with an east and north direction, right? So it's like bird's eye view on the Coriolis effect, and then this one is actual vertical structures. So the point is that if we look down on the Earth, we see circular structures that appear flat or are encompassing the sphere of the Earth. But when you're on the surface of the Earth and you look off towards the horizon, if there's say dust in the air, you'll see circular structures that go up above the ground. So we have lots of different circular structures on different axes driving wind throughout the planet. Right? Here is the Coriolis effect shown at the overall scale of the planet with those deflections occurring near the poles and then their overall effect leading to basically wind that runs along the equator. All right? And there are actually very low winds along the equator, the doldrums, which means there's very little wind directly along the equator. Okay? So at the equator, rising warm, moist air creates a zone of low surface pressure, which is the doldrums, right? This is very, very little wind. The trade winds exist anywhere off the equator up to an angle of about 30 degrees, or a latitude of 30 degrees relative to the equator. At 30 degrees north and south, we have air cools and sinks to create dry air and high pressure. These are called the horse latitudes. This is where deserts and westerly winds exist, or at least the westerlies exist between the latitudes of 30 to 60 degrees. At 60 degrees north and south, so above and below the equator, we have cool, dry air that meets warm, moist air to create zones of low pressure. This is the polar front. This creates polar easterlies that go all the way up to the pole in terms of their directions. So we have predominantly west winds in the middle latitudes and predominantly east winds in the very high latitudes. To put that in context, the latitude of, say, Northern California is around 38 degrees, so well within this region here. The prevailing westerly winds are affected by the Coriolis effect by the deflection of winds. To the right in the northern hemisphere and left in the southern, to the left in the northern and right in the southern, or laterally towards the poles, or just always westward. Well, we can definitely rule out always westward. We saw examples of it going both west and east. Well, indeed, it's to the right in the northern hemisphere and the left in the southern hemisphere. Let's see that again in the picture, right? So to the right, we have over here in the northern hemisphere and to the left in the southern hemisphere. All right? So the prevailing winds in North America are westerly. They blow from west to east, right? They're within the region of the westerly winds. Westerly winds contribute to cooling the western coast in the winter and warming in the summer, or in the summer and warming in the winter, or so that the temperature is the same all year long, or is it and making temperature variation more extreme? Well, it's actually that those winds are cooling the western coast in the summer and warming it in the winter, right? So basically making more mild winters and more mild summers in general. Okay, well, what about ocean currents, right? If we're talking about global currents of air, aren't there global currents of oceans? Absolutely. Ocean currents are streams of water that move relative to the large oceans. Like the atmosphere, oceans have several vertical layers: surface zone, transition zone, and deep zone, with different temperatures and different characteristics, just not nearly or even close to as much variation in density. The atmosphere has those drastic variations in density and different absorbed energy from the sun. Ocean, I guess, a little less dramatic there, but still some defined zones. So surface currents, as we spoke about already, are created by wind, really kind of contact of wind making a difference. But surface ocean currents correspond to the direction of the prevailing winds. But beneath the surface, things change, right? There's something called Ekman transport that says the Coriolis force causes water currents to deflect up to 45 degrees. So as you go down in depth, the direction now is not the same direction as the prevailing wind. It is about 45 degrees off from that direction. Right? So factors that influence ocean currents, well, for short distances, the wind is the strongest factor. However, for long distance, that Coriolis force comes into play. That Coriolis causes the surface currents to turn and twist into semicircular whirls called gyres. The northern hemisphere gyres rotate clockwise, southern hemisphere gyres rotate counterclockwise. And this obviously affects ship navigation. Gyres cause heat transport from equatorial regions to higher latitudes. The Gulf Stream current carries vast quantities of warm tropical water to higher latitudes. So we can see in this heat color-coded image, Florida shown here, right, and the eastern United States up into Canada up here. Well, we see warm water represented as red flowing up and meeting this cold water, right, and then having a mixing effect. But also before that warm water has a mixing effect with the cold water, we see that there is warming of fairly northern shores, right? So warm water getting pushed up fairly far north, obviously creating a more mild climate on the eastern coast than it would have otherwise. So years in which the trade winds fail to strengthen are called El Nino years, and El Nino in the southern oscillation influences the climate on both sides of the Pacific Ocean. Deeper waters are driven not by winds, but by gravity. The wind stops mattering as we go deep into the kilometers of depth of the ocean. Polar water freezes, increasing the salinity of the liquid. The cold, salty water continuously sinks to the ocean bottom. It's denser. The sinking water pushes the deep water out of the way, causing the bottom water to flow outward along the ocean floor. There's constant motion away from the poles along the ocean floor. A combination of deep water mixing by the ocean floor tidal stirring and upwelling due to favorable winds, right, creating regions of low pressure where big currents can get pushed up, brings the deeper waters slowly back up to the surface. This conveyor belt process may take thousands of years. It's that slow and on such a huge and slow scale, all right? But eventually the water from the deep ocean will mix back up to the surface. It doesn't just end up there and stay there forever. Well, there we have our introduction to a little bit about oceanography, Earth's climate, overall motion of the atmosphere, and a bit about the composition and layers of the atmosphere, and a little bit on the ocean. Well, I hope this lecture has been interesting and informative. Thank you so much for watching.